Welcome to Who Shaves the Barber, a weekly podcast where we explore paradoxes, thought experiments, and other pointless problems. I'm William Nava. This is part 2 of my interview with Professor Graham Priest. Last week, we discussed problems of unity and regress. While I recommend you listen to that episode first, because we make passing mentions to that topic here, it is not essential. Today, we take on an entirely new topic, that of the Sorites Paradox. First, for people that don't know what it is, can you give a quick explanation of what the paradox is?
Yeah. Okay, so there's this bunch of predicates in most natural languages which are vague to a certain extent, or in a certain sense. And the sense is this: if it applies to an object, and then you tweak the object just a little bit, then the predicate still applies. So, take the predicate is drunk. So, you're stone cold sober, you haven't had any alcohol for 5 weeks, right? And I give you one nanogram of alcohol. What's a nanogram? Is it 10 to the minus 6? That's a microgram. Nanogram? 10 to the minus... Okay, well, whatever.
I can't convert things to scientific notation off the top of my head, so, but it's very small.
Well, look, if you put it on a saucer, it'll be too small to see. Okay? But there it is, and you drink it. You're still sober, right? You're not drunk. And in general, whatever state you're in, whether if you're sober, and giving you this sort of quantity of alcohol, which you can't even damn well see, won't suddenly change you from being sober to being drunk. Okay. So being sober or being drunk sometimes they're called tolerant. It's just another way of talking about the fact that you can, if the predicate applies, then if you tweak the object a little bit, and the tweak in this case is giving you this really minute amount of alcohol, then the predicate still applies. So crucially, giving you 1 nanogram of alcohol is not going to turn you from someone who's sober into someone who's drunk. All right. Now, if you think for a moment, you can see where the problem is coming from. So I take you, and I give you 1 nanogram of alcohol. You start sober, I give you 1 nanogram, you're still sober. Then I give you another nanogram, and you're still sober. Then I give you another nanogram, and so on. And at no stage does giving you 1 nanogram turn you from being sober to being drunk, being not sober. But of course, after you've imbibed, 5 or 6 liters of the damn stuff, you're under the table. You're not sober anymore, for sure. That's the Sorites Paradox, because how you can have a sequence of small changes which make no difference, but if you keep performing them, you do get something that's different. That's the Sorites Paradox.
Great. So before going into how to solve it, I think that that's it's clear what the paradox is. I kind of want to take a little bit of a detour and then come back to the problem of how to solve it. Can you, because I want to talk about it through the lens of the principle of uniform solution that you've, is that something that I don't know if that's something that you originally proposed. I know I've heard of it from you. But yeah, can you talk about that principle?
Yeah. Yes, that was something I coined in a book way back in the 90s, The Principle of Uniform Solution. And it says, crudely, same kind of paradox, same kind of solution. That seems about right, if you've got wildly different kinds of paradoxes, paradoxes self-reference, Zeno's paradoxes, there's no reason why you should expect to have the same kind of solution. But if you've got 2 paradoxes which do seem to be of the same kind, then you should expect to treat them the same way. So come back to our friend the liar paradox. It uses self-reference, but there are many different ways that you can obtain self-reference. You can obtain it by demonstrative, that pointing. You can obtain it by a definite description, the sentence written on the blackboard. You can obtain it by, technically by a process of Gödel numbering. So, but how you obtain self-reference doesn't really seem to be important. It would be crazy to say you give one solution if you use a demonstrative, that, another solution if you give, if you obtain the self-reference with a description, the sentence written on the blackboard. That's what the principle of uniform solution is telling you. If you got the same kind of solution, then you damn well expect to have the same kind of, so if you got the same kind of paradox, you damn well expect to have the same kind of solution. Now, that puts a lot of weight on the notion of what it is for two paradoxes to be of the same kind, and that's not at all obvious, okay? However, once two paradoxes are agreed to be of the same kind, then it's kind of natural to suppose, hey, they must be treated in the same way, so you better have the same kind of solution.
One thing that, so I've thought about this problem of, how do you identify whether two paradoxes are of the same kind? One problem that, one way of looking at this problem that I've thought of is there's a sense in which, trivially, all paradoxes to some extent are of the same kind, since they all share the
paradoxes. Yeah.
They're all paradoxes. And so whatever it is that two paradoxes share in order for this principle to apply, it can't be that broad, right? Sure. And so there's sort of levels of kind of specificity that this point seems to suggest.
Sure.
Would you say that maybe one way of addressing this is that if we could identify these sort of levels of specificity at which the structure is shared, that the way in which the solution needs to be the same also should sort of match at that level?
So I think that.
Yeah.
Well, I mean, maybe I'll answer that too quickly because maybe I didn't understand your question.
Well, let me put it this way, just to make sure that I'm being clear. All paradoxes share some properties, the properties required for being a paradox.
Well,
but then all solutions to paradoxes also share a property, which is that they all either reject one of the, put it this way, they all either reject one of the premises, accept the conclusion, or change one of the rules of logic or whatever. So the shared structure is very broad, and then the shared structure of the solution is also very broad. And so as you identify a shared structure at more specific levels, you should also identify a shared solution at a more specific level. Does that make sense?
Yeah. Okay. That's not what I thought you were going to say originally. So I agreed too fast. Look, what you're saying may be right. I mean, what you're pointing out is there are a number of different levels, and you should be able to apply the principle at every level. I'm not sure I have a view on that. I'd have to think about that some more. But that's not what I intended for sure. Because there's one level which I take to be privileged. Because when you analyze a paradox, if you analyze it carefully, you can usually see that there's some kind of mechanism that's driving the contradiction. I know it's a bit odd to talk about mechanism in this context because we're not talking about a piece of machinery. But, the notion of structure makes perfectly good mathematical sense. So, often mathematicians will talk about, say, two algebras having the same kind of structure. And the level at which I think you should apply the principle of uniform solution is at the structural level. So first of all, you need a clear analysis of what is structurally driving the contradiction. Once you've located that, then if it's the same structure in each case, then you should do the same thing in response to the structure. Okay, now, again, that puts a lot of weight on this notion of a shared, or what structure is really driving the paradox. And the answer to that question is not obvious either. But that's something you have to try to nail down if you want to apply the principle of uniform solution.
Okay. So then let's dig a little bit more into this. Your diagnosis of, you have a kind of a diagnosis of shared structure with certain paradoxes, namely the paradoxes of self-reference, such as the liar, which is the enclosure schema, right? So you use this thing called the enclosure schema to kind of identify that shared structure that's driving the paradox. And again, this gets a little bit into sort of formalisms, but can you sort of broadly explain how this idea of what the enclosure schema is and how it explains how the paradoxes of self-reference work?
Okay, so let me do this. First of all, let me say that the enclosure schema is not an argument for dialetheism. Okay, it's just an argument to try to show that a bunch of paradoxes have the same mechanism, the underlying structure. Okay. What you do about that, well, that's a separate story. Okay, now the enclosure schema is this. If you analyze the paradoxes that seem to be in this family, like the liar and Russell's paradox, and there's a whole bunch of these things, what you see is going on is this, and this is not my observation, it's actually Russell's. Russell's analysis wasn't quite general enough, so I tweaked that to get the enclosure schema. But let's keep things simple. Let's talk about Russell's analysis in the first place. What's going on in all these paradoxes is as follows. You've got a totality of a certain kind. All sets, all truths, big set. And there's an operation which you can apply to subsets of that totality. All right? So let's take the set of all truths. Let's take a subset of that. So you've got a bunch of truths. Right. Now, there's an operator you can apply to that bunch to give you a new thing. Right? You can say, this sentence is not in that bunch. So call that subset X. Then you've got this operation which forms a sentence which says, hey, I'm not in X. In the book Beyond the Limits of Thought, where I talk most about this stuff, I call this operation a diagonalizer because when you look at how this works in set theory, it's often implemented by a process of diagonalization. But I don't want to go into that now, okay? That's too complex for you. The crucial thing is for any subset of these guys, in our example of truths, there's an operation which you apply to it to give you a new sentence in this case. And this, when you apply this operation, you get something with two properties. First of all, it takes you out of the subset, right? So you've got these bunch of truths, you've got that, and take any sub-collection of that, you apply the operation, and it gets you something which is outside that set. So I call that transcendence because it just transcends the set. The second the second property is that when you apply this operator, even though it takes you outside the set, you stay in the original totality. Okay? So I call that property closure just because the operator, this totality you started with, is closed under this operation. All right. So, got this big picture, all big set, maybe the truths. You take any subset of that, you apply an operation to that subset, and you get a new thing which is outside the set, but which is within the original totality. Okay. And when you look at particular paradoxes, you sort of figure out how the diagonalization actually has these two properties. So this is all very abstract, right? But we're talking about structure here. Now, if that's what's going on, what's going to happen when you apply this operator to the original totality you started with? When you take the whole totality, which is sort of trivially a subset of itself, subcollection of itself, and you apply this operation, because of transcendence, it's got to take you out of that set. Because of closure, you've got to remain within the set. So when you apply this operation to the whole set, you're going to get something which is within and without the set, and that's the contradiction. And if you look at the structure of the various arguments, you can see how they fit this pattern. But what's doing the real work is this operation which satisfies transcendence and closure. It lifts you out of any totality you're in, but keeps you in the kind of the big totality you started with. So that's the enclosure schema in a nutshell.
Right. So that makes sense. In the case of the liar, right? So I don't want to go into I don't want to explain all like you said, I don't want to go into all of how the diagonalization works and everything, but that operator, what it does is it outputs a sentence that says, I'm not in that subset that this operator just acted on, right?
Correct.
And so that operator already has in its definition an element of self-reference, right?
Correct.
It's already outputs a sentence that it already involves self-reference.
Correct.
So, well, actually, before following with that train of thought, can you say a little bit about how, because I think everything you've said so far makes perfect sense. What might seem a little bit surprising is then that you make the claim that the Sorites paradox fits the same. So again, without going necessarily into all the formalisms, can you explain why this general structure you've put together fits the Sorites paradox?
Yeah. Look, first of all, I agree it's surprising. For many years, I thought paradox of self-reference and the Sorites paradox were just completely different kinds of things. And I changed my mind. And what changed my mind was the fact that I suddenly saw that it fits the enclosure schema, the Sorites. And given that I was already committed to a dialectic solution to the paradox of self-reference, then, okay, I thought, well, I better have a dialectic solution to the Sorites paradox as well. All right. So, how does the Sorites paradox fit the enclosure schema? Let's do this as an example. Let's do this for colours because it may be easier to visualize. So it's easy to construct a Sorites with colours. So take some sequence of continuum of colours. So you start off with something that's red at this end, and then it's slowly the colour changes. Might be over 1.5 miles. Okay. Then it goes sort of to slightly less intense red, and a little bit mauve, and then sort of maybe purple, and then a sort of reddish blue, and ends up as blue. So you've got this very gradual change from red to blue, but it's spread out over 1.5 miles. All right, so you cut it up into little strips 1 inch wide, okay, such that if you look at one strip and the adjacent strip, they're indistinguishable. They look as though they're exactly the same colour. All right. So now you can see how you can apply the Sorites, because you start with this thing that's red. You move to the next strip, which is indistinguishable in colour, so it's got to be red too. But then you go to the one next to that, and that's indistinguishable from that, so that's got to be red too, and so on. And so you conclude that this thing which is sort of sky blue is red. Okay, so just think about that example of the Sorites. All right, how do you apply the enclosure schema? Well, first of all, as I said, you've got to have a totality of stuff, right? Take the totality to be the red strips. Okay. Now, suppose you've got, next thing you want to know is what the operation is, which has these properties of transcendence and closure. So let's take any bunch of those red strips. There's got to be a kind of an end one, okay? Because, you know, each one is 1 inch long, it spreads for 1.5 miles, but, you know, if you take any bunch, it's finite. So there's got to be a last one, sort of closest to the blue end. All right. The operation is take the next one to the right, or the next one towards the blue end.
So you start with, okay. Let me just make sure that this is clear. You're starting with, you're calling it a bunch, but this is sort of analogous to what we were calling a subset when we were talking more abstractly, right? Sure. You're taking a chunk of this large strip, and then what the operation does is it identifies the one of that bunch that is closest to the blue end, and then it outputs the next one over.
The next one. Mm-hmm. All right. Now, this satisfies transcendence, obviously, because you started with this bunch and you defined it as the first guy that isn't in that. So it's got transcendence. But this tolerance property gives you closure as well, because, you know, if it's right next to a guy that was red and it's indistinguishable, it's red too. So remember, our original totality was totality of red strips, red bits, okay? So because of the kind of tolerance of that predicate, this guy, since it's next to a red guy, must be red. Okay, so if you define the operation like that, it satisfies transcendence and it satisfies enclosure. Okay, so it fits the schema.
And then the paradox is generated when the bunch that you take is defined as all the red ones.
Sure.
Right, because
so at some stage, you're going to get something that's red and not red. So, you know, when people look at the Sorites, I might just say, you know, logicians have been arguing about this for now 30 or 40 years, and there's no agreed upon solution, none whatsoever. But a very common thought is you've got this transition, maybe the red-blue one. You can say what things are at one end, they're red. You can say what they are at the other end, they're blue. And then there's this kind of bald line area in the middle where you're not quite sure what to say. And many logicians think, well, the things in the middle, say that it's red is neither true nor false. Oh, well, that's, you know, plausible because, after all, the middle seems to be symmetric with respect to the two ends. So this is red, it's true. This is red, it's false. What's symmetric between truth and falsity? Well, it's neither true nor falsity. You know, it relates to both ends the same way. That's true. But that's being neither true nor false is one way to achieve symmetry. Being both true and false is another way. That's the dialethic solution. Now, most people, if they've preferred a solution of this kind, have gone with the neither solution, not the both solution. But the both solution is the dialethic solution, and that's the one I think is right. And I think I came to accept that because of the enclosure schema business, but I think there are independent arguments with this as well, but that's another story.
So I have some potential objections to interpreting this result in this way. I'm curious to hear what you would think. One is that in the enclosure schema, the operator does most of the work, if that makes sense, right? The totality and the subset, all of that is sort of like a kind of setup, and then the operator really does the work. So in the case of the liar, the operator itself has self-reference involved in it. Right? The definition of it actually involves self-reference already. In the Sorites, it's not that's not as obvious. whether there's self-reference involved in the operator.
There's no self-reference of the same kind. Okay, it's not a paradox of self-reference. So enclosure paradoxes have paradox of self-reference as a kind of subcategory. But why they're in the same class is precisely because they have the same underlying structure. You've got this operator satisfying transcendence and closure. And once you understand how the operator satisfies those properties, how it sort of pulls you out of the set but keeps you in the totality, then it's obvious why you get, at the limit, an immovable object meets an irresistible force. Bang. Okay, and you can see why that happens once you understand how this operator, the diagonalizer, does what it does. So as you said, that is the key to understanding these things. And in the case of the liar, there's a very, very opposite example of self-reference. There isn't in the case of the Sorites.
So I guess the idea behind this being an objection is that because one of them has self-reference and the other doesn't, you could say, well, look, the operator in this, which is the thing doing the real work, has a sort of different structure in one versus the other. One of them is self-referential, the other isn't. And so maybe that should be enough for us to say what's driving the paradox is different enough that we shouldn't expect the principle of uniform solution to apply.
This is a very natural thought. I mean, it comes back to one of the first comments I said. How do you tell when two paradoxes are of the same kind? And you've pointed to a disanalogy and said, well, this is sufficient to show that, there isn't. I think this disanalogy is superficial because I think what's the mechanism is actually driving the contradiction is precisely the fact that you've got this operator which levers you out of a totality whilst keeping you in the same totality. Now, not all paradox of self-reference use the same kind of self-reference as a liar. So let's look at something which is... Sorry, can you hear that?
I can, but no, I'm surprised I haven't gotten it yet. As you know, I live in New York, so I get them all the time. I totally understand.
All right. No, well, I'm in downtown Melbourne, right? And it was, I don't know, some emergency vehicle going down the high street. All right. So there are paradoxes of self-reference which look a lot more like the Sorites. Let me give you one. This is called König's paradox because it's a paradox which was discovered by a Hungarian mathematician, König, in about 1910. It's a paradox of set theory. So to understand it, you've got to understand something about set theory. So forgive me if I take, a few minutes just to give you the kind of basics you need to understand.
Please.
So think of ordinary counting numbers to start with. 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. There's no last one, okay, as you learn about the age of 6. All right. But in set theory, you can have a construction which actually extends these numbers into the infinite. Okay. So after 0, 1, 2, 3, 4, 5, there's no last one of those, but there's one that follows all of them. And this is, mathematicians call these ordinals. And they usually call this guy omega by the Greek lowercase letter. And it's the least infinite ordinal. So far, so good?
So omega, right, you said?
Yeah.
Is an ordinal. It's infinite, and it's but it's the least infinite one. Okay, yep. Following you so far.
Okay, but of course, once you've got omega, you can have omega plus 1, omega plus 2, blah, blah, blah. Then you have 2 lots of omega, 3 lots of omega, lots of omega, etc., etc., etc. It goes on and on and on and on and on. Okay. So this is a structure that set theorists call the ordinals. And it's sort of what it does. It's kind of mind-blowing when you meet this stuff for the first time, that there's actually a structure, a determinate structure in the infinite. I mean, this blew a lot of people's minds 120 years ago when Cantor proposed this. Anyway, you've got these ordinals, which are an extension of the counting numbers into the infinite. Okay. Now, one of the most important properties of the ordinals is this. In fact, it's sometimes used as a partial definition. Think about the counting numbers for a start. You can't have an infinitely descending sequence of counting numbers. Right? Choose a counting number, 37. Now, can you have an infinitely descending sequence? Well, it's 36, 35, 10, 2. You've got to hit 0 sooner or later. Right? Now, the ordinals preserve that property. You can't have an infinitely descending sequence. So any bunch of ordinals must have a least member. Otherwise, if it didn't have a least member, you could have an infinite regressive ordinals. Right? Just as if I take any set of counting numbers, there's got to be a least number. Okay, it might not be 0 because 0 might not be in there. But, okay, there's got to be at least one because you can't have an infinitely descending regress. Same with the ordinals. You cannot, every set of ordinals must have a least number. This is something called well ordering. All right. So far, so good. Now, question: how far do the ordinals go on? Forever and ever, right? It's really hard to give an intelligible answer to that question, both mathematically and philosophically. But however many there are loads and loads of them, more than you can possibly refer to by a noun phrase in English. And you can prove that. That's a sort of simple combinatorial argument, because the things you can refer to by a simple noun phrase in English have the lowest size of infinity, whereas these ordinals get bloody large, much, much larger than that. So consider all the ordinals that can't be referred to in that way. There's got to be stuff like that, just because there's so many of them. By the well-ordering property, there must be at least ordinal you cannot refer to. Since it's the least ordinal you can't refer to it. Hey, what have we just done? Refer to it by the least ordinal you can't refer to. All right, so that's König's paradox. This thing is both referable and not referable. Now, the least ordinal you can't refer to doesn't apply self-reference in any obvious way. Okay, and in fact, if you think about it, when you construct this funny number, what you're doing is you're taking all the referable sentences and then taking the next one. That's not exactly unlike taking all the a bunch of red things, and then taking the next one. Okay, so in this case, the operation, which is taking you out of the totality, is this: you got this totality of referable ordinals, and the operation is, hey, take the least which is greater than all those. And that's a bit like taking the next strip on the Sorites progression. So you can see that the König's paradox is actually a paradox of self-reference. It standardly gets classified in that way, but it's not a million miles away from the Sorites paradox either.
What occurs to me when you describe that is that what the Sorites and Königs share is, I don't know if this is the right way to call it, but something like the successor operator.
Well, it's not the successor, it's the least number greater than. So, I mean, when you take a bunch of things, bunch of ordinals, it might not have a last member. So there isn't, what you choose is the least ordinal greater than all those guys. That might not be the successor or anything, because omega, the least infinite ordinal, is not the successor of any finite number, any counting number, because for any finite counting number, there's a greater one. So omega is not a successor. It's simply the least ordinal that's greater than all the finite ones.
I see. The sort of thought that I had with this successor point is that there's some kind of a progression going on, and that the operator essentially, part of what it's doing is it's calling you to the next one.
Yeah, it's sort of jumping you out. That's transcendence.
Mm-hmm. Now, isn't there something self-referential about having to say the next one? Because it's the next one to the one you're starting from, so that there's a kind of implicit self-reference?
Maybe. Look, this is a bit murky just because the term self-reference isn't a particularly well-defined term. Sometimes you can recognize it sort of pretty obviously. Sometimes it's not so clear. So there isn't really a well-established definition of self-reference. It would be very nice to have that, but I don't know that there's one that everybody agrees with. Just because there are cases where it's not sort of clear whether what you've got is self-reference or not. So this is slightly off on a tangent, but Steve Yablo proposed a paradox now called Yablo's Paradox.
I was just thinking of that as well. It has that same kind of...
Steve claimed that, so it involves a regress of sentences. Each sentence in the list refers to all the ones that come after. So prima facie there's no self-reference, okay, because each sentence refers to a bunch of other guys. Okay, I mean, I think there is self-reference in there, but it's not obvious. You have to look at kind of the structure of how you generate this sequence. That's certainly far too technical to go in for here. But whether or not Yablo's paradox employs self-reference is a moot point. Steve thought it didn't. Some people like me think it does. That's because no one's ever actually sort of pinned down the notion of self-reference in a very precise definition.
Okay. All right. So let me kind of bring it now back to the Sorites, because I think it's clear, how the enclosure schema sort of gives you a reason to think, well, the solution that I've got for the liar paradox should be the same kind of solution that I have for the Sorites. So you have a solution to the Sorites that involves paraconsistent logic, and involves essentially, as I remember, a kind of a middle area where in this strip, let's say, of red things that you talked about a moment ago, there's going to be a middle area where the predicate both applies and doesn't apply. Right?
Well, it applies and its negation applies.
Applies and its negation applies. Okay. So I guess the last thing I'd like to talk about here is that right away it suggests the idea of a cutoff.
Sure.
Right, which is the idea that there's going to be some precise boundary between where the things are just red and where the things are both red and not red. And then there's going to be another precise boundary between where they're both not red, and then where they're just not red.
Sure.
So what is your... So that, I think, is something that remains kind of counterintuitive, even if we accept everything else about your solution.
Yeah.
What is your kind of, again,
right.
What is your story about that?
So look, you're dead right. If you come back to the original Sorites, the thought that there should be a precise cutoff point where the sequence changes from red to not red or sober to not sober, intuition rebels against that. It rebels against the existence of a cutoff. That's what's driving the paradox. And if you partition the sequence not into the trues and the falses, but into the trues, the falses, and the boths, or for that matter, the trues, the falses, and the neithers, you've made matters worse. You haven't got one cutoff, you've got two now, as you explained. All right. So there's a lot more that needs to be said here. And I think that it's this. If you look at all the mooted solutions to the Sorites, they all invoke a cutoff of some kind somewhere. Whether it's done in terms of neither true nor false or fuzzy logic, or and there's sort of a reason why there must be a cutoff, because hey, you've got this finite progression, and it's got to change by the time you get to the end. Because you've got a finite progression, it's got to change somewhere. So I reckon that everyone who tries to solve the Sorites paradox is stuck with a cutoff. That's a fact of life. Just get used to it. So a solution to the Sorites does not involve getting rid of cutoffs. I think you can't do that. All that a solution to the Sorites can actually do is explain why that's so bloody counterintuitive. Now, given what you think is going on in the Sorites, you're going to offer different explanations of why we found it counterintuitive. So Tim Williamson, for example, has what he calls an epistemological solution to the Sorites. There is one cut-off between true and false, end of story, but you can't know where it is. That's why you find it counterintuitive. Yeah, it's an attempt to explain this. My solution to the why we find the cutoff counterintuitive is not epistemological. It's that, if you've got, let's take a very simple case. Let's take the cutoff between being read only and being read and not read. Okay? We find it counterintuitive there's a cutoff there just because they're both read. That's sort of the first move. Now, that's obviously a different kind of explanation. Now, where the dialectic moves is this, we want to know which is the best explanation. Okay, and so where the discussion goes at that point is, whether or not you look at the various explanations to be given and see which is preferable. I happen to think the dialectic explanation is preferable. I don't know if it's kind of profitable to go into that here because it raises a number of issues. But that's where the answer to your question goes.
Okay. That makes sense. Is there an aspect of this that you think is partially an appeal to intuition? Where, I think at least as far as the dialectic part of it, there's I think an appeal to intuition in the sense of saying that people would probably be comfortable saying, yeah, that looks red, but also doesn't look red. Is that kind of a sort of intuitive thing, part of what justifies you?
No. It's sort of collateral support. Often some philosophers have claimed that no one in their right mind would accept a dialectic solution because people just don't say these kinds of things. But in fact, there is empirical evidence out there to show they do. Of course, people will say all kinds of things. So the fact that people will say, well, it's kind of red and not red, doesn't prove a dialectic solution, but it does prove that, you can't just simply say, well, no one in their right mind would say this, because most people that are in their right mind, at least when it comes to judging colours. Let me just make a final comment, because it does sort of refer back to something we were talking about earlier, which is this. When you sort of work out the dialectic explanation of why we have this intuition that there's no cutoff, and you sort of articulate all the details, what you suddenly discover is that, suppose you've got two adjacent strips. This one's red, this one's red. So to say that this is red has a truth value, say that this is red has a truth value, both things have the same truth value. Now, that's not obvious. It falls out of the details. That if you have two consecutive strips, to say that one is red has the same truth value as the fact that the other one is red. Okay. Now, if you think about it for a moment, you can see that identity of truth value is not going to be transitive, because each pair of statements has the same truth value as the one next to it. But transitivity is going to fail, because otherwise it will work all the way down. So that actually, I mean, even though I know we were talking about something that was completely different, the transitivity and the non-transitive identity is sort of rearing its ugly head in both of these phenomena.
That makes sense. Yeah. Okay. Yeah. Thanks for adding that. That actually does help. I'm going to leave the Sorites here. I think we've gone fairly deep into it, and again, I don't want to go into sort of like formalisms and stuff. So yeah, we've gone fairly deep into two separate questions, which I really appreciate. I'd like to ask you just two more broad questions. The first is, in one, for example, you talk a little bit about Heidegger when you talk about nothingness. In other works, you've talked about Hegel, because he talks about he talks about contradiction quite a bit. I know there was once a conversation you and I had where you mentioned Derrida a little bit. So what I want to ask you is, there's obviously this perception of there being this huge split between the analytic tradition and the Continental tradition, and you're probably one of the few people that I've talked to who is sort of heavily works within the analytic tradition, but then you'll also go just sort of bring in some of the Continental guys here and there. I'm curious to hear your perspective on to how you account for this split, to what extent you think it's really there, and sort of what do you think is going on with that split?
Well, you're certainly right that many people perceive a split. As just a matter of fact, that perception is now disappearing. I'm not the only person on the so-called analytic side who works on the Continental side as well, and I know plenty of people who work on the Continental side that work on the analytic side as too. Many of my friends in Italy and Germany and so on. So the perception that this is some kind of important distinction, I think is slowly disappearing, and good bloody riddance. Because I think that the perception that there is an important distinction here is driven, well, it's partly driven by turf wars. So, you're in an analytic department and someone wants to read Heidegger, and people say, oh, naughty boy, naughty girl. So you feel marginalised. Okay, of course there's going to be a turf war. So what I'm doing is just as good as what you're doing. It's also partly driven stylistically, because clearly Heidegger does not write the way that Saul Kripke writes. Fine. You don't need to know much about the history of philosophy to know that there are many, many ways of writing good philosophy. Aristotle is not Kant. Kant is not Hume. Hume is not Wittgenstein. Wittgenstein is not Kripke. Kripke is not Derrida. And for that matter, none of these guys is the same as Dogen or Nagarjuna or all the guys in Eastern philosophy. That's another boundary that's coming down too. So if you grow up, cut your philosophical teeth, reading philosophy as written one way, and you start to read it in another way, you're going to go, oh, I don't get that. Okay. And, many people who are trained by just reading Frege and after, find it very difficult to understand, reading Heidegger, because he writes in a way that you're just not used to. But, hey, you want to get used to it. Many of my friends who work in the continental tradition say, "Oh, I find reading Heidegger easy. Kripke, that's hard." It really is just a matter of what you're used to. Now, there's no real philosophical divide here. There are often people from the different parts of the tradition are usually dealing with well-recognized questions on both sides and so on. They may approach them differently, they express themselves differently, but hey, that's not significant philosophically. Which is not to say that there isn't a lot of crap continental philosophy out there. There sure is. There's equally a lot of crap analytic philosophy out there. And they tend to have different vices. Crap continental philosophy tends to be sort of vague and obfuscationist and pretentious, whereas crap analytic philosophy tends to be minute and boring and losing the wood for the trees, and so I'm not saying that that there isn't crap philosophy on both sides of the divide. There sure is, but there's bloody good philosophy on both sides of the divide. Okay, I don't know. Heidegger is a great philosopher. I don't know which side of the divide you want to put Wittgenstein on, but he usually goes on the analytic side. Great philosopher. As a philosopher, you try to learn from the great philosophers of the past and hopefully, do something original with new thoughts. But that means that you've got to read the good philosophers in the history of philosophy and get to grips with their ideas so that you can see where to take things from there. So we shouldn't be concerned about reading analytic philosophy, continental philosophy, or Western philosophy or Asian philosophy. We should be concerned with reading good philosophy. And that you find good philosophy, indeed great philosophy, in on all these traditions.
Fantastic answer. That's exactly how I feel about it as well. Great. I have one more question for you. So, in some conversations that you and I had, I know that you've been kind of getting into the philosophy of anarchism. That you're also planning to write a book on anarchism. Is that right?
Yeah. Not exactly. The next book that I have in mind is an attempt to bring together Buddhist ethics with left-wing European political philosophy. So that'll be Marx, the anarchists, and whatever else occurs to me between now and when I write.
Okay. Yeah. So actually, that was kind of the question that I wanted to ask you, because it seemed that anarchism would be such a kind of digression, given most of the things you've worked on so far. I was going to ask you sort of why something so completely new, but it seems like it's sort of something that you're getting into through your interest in Buddhist philosophy?
Not exactly, no. Look, I've always had an interest in political philosophy. I mean, I've had an interest in politics, right? I have an interest in political philosophy. I've been reading Marx for years and years and years, and have a great deal of sympathy with him. I've never written much about political philosophy, partly because my expertise, such as it is, has been in other areas. But, it struck me that it's about time I wanted to think more seriously about this. And the Buddhist ethics is an introduction into that, because one of the things about left-wing political philosophy in the West, people like Bakunin, Marx, Kropotkin, is they're great political philosophers, but their ethical theory is a bit sort of impressionistic. None of these guys really has a serious ethics. You get hints. But Buddhism certainly has a very strongly articulated ethical philosophy. And it kind of struck me that you can see the Buddhist ethical stuff in many ways as complementary to the left-wing European political philosophy stuff. That's kind of odd. But there's this kind of strange quote, but what you'll find if you Google Dalai Lama and Marxism, where Dalai Lama says, politically, I'm a Marxist. And you think, what? He's not stupid. He's a bright guy. If he's a Marxist, there must be something going on there. Well, that's what I want to explore. And as you say, it's a new departure for me, but then, everything I write, in some sense, is a new departure. So it's one I'm looking forward to a lot.
Great. All right, so thank you so much for doing this. I really appreciate that I said this before, but again, I'll say it, I really appreciate that we were able to get relatively deep into some of these problems and still kind of avoid getting into any of the formalisms. So, I consider that a bit of an achievement. So, thank you so much for doing this. And that concludes today's episode of Who Shaves the Barber? Next week, I'll be speaking with dream analysis and lucid dreaming expert Brian Nuckols about the ontology of dreams. Again, I'm William Nava. You can check out other episodes, as well as my other philosophical and artistic work at williamnava.com. And if you'd like to subscribe to this podcast, go to williamnava.podbean.com. Thank you so much for listening.